Hi, everybody. So today I want to talk a little bit more about sequences. And it turns out that sequences have limits, much like functions do. And just like functions, all those function laws and all the function rules and all that stuff with function limits that we had also apply to sequences. And so what we're going to do today is just mostly review the limit laws and stuff for functions. So in particular, there's a correspondence between the limit of a function and the limit of a sequence. So if the sequence is described by f of x, so f of n is the nth term of the sequence, then I can take the limit as x goes to infinity of f of x and I get L. And if that's the thing, L, it might be positive infinity, might be negative infinity, might be finite, but that will be the limit of the sequence as well. So if the limit of this function is infinity, the limit of the sequence will also be infinity. So it'll be a divergent sequence. If the limit of the sequence or the function is 15, the limit of the sequence will also be 15. And so we can sort of do that limit as we want. So in particular, all that limit stuff that we sort of did in Calc 1 at the beginning is going to follow through here to Calc 2. And you'll notice that this limit, last time I mentioned that this limit is different than the limit that we had before. So the limit as n goes to infinity of an, this limit only takes into account all integers. So integers are running to infinity, but notice that as x goes to infinity, there's always an integer beyond that x, that whatever value that x takes that is bigger, that's an integer. And so as x goes to infinity with the real numbers, so you go to pi, there's always something bigger than that 4, say, that is an integer. And so then these limits are actually going to be the same. So they go the same place. It's really nice. All right, so what we have here for this, we have some limit laws. So for the limit laws, we're just going to apply the same limit laws that we had for functions. This time we're just going to phrase things in terms of sequences. So the limit of the sum or difference of two sequences is the sum or difference of their limits. So in other words, I'm giving you sort of two functions, two sequences here. Sequence an has limit a, sequence bn has limit b. So the limit of the sum of those two sequences is the sum of their two limits, or difference of two limits. And then the limit of a product, a multiple of that sequence is the multiple of that limit, and that works for any real number c. The limit of the product of the two sequences is the product of their limits. The limit of the quotient is the quotient of their two limits, the limit of the quotient of their two limits, provided that the denominator is not 0. So we cannot have the denominator be 0 here, and so that's where we sort of would screw it up. If that bn goes to 0, then this whole thing doesn't work out with the quotient. Okay, so those limit laws we kind of brush over a lot in Calc 1, but we can brush over them here as well. We can kind of say, okay, so it doesn't really matter. I just have to do those two limits separately and then just add them or subtract them or multiply or divide them as I want. Other tools that we can use that are really nice are things like L'Hopital's rule. So L'Hopital's rule, so that if I've got two sequences described by two different functions, f of x and g of x respectively. So f of x describes an, g of x describes b sub n. Then as long as the two limits either both go to an infinity, and they could go to different infinities, it could be positive infinity on the top and negative infinity on the bottom, or negative and negative, or positive and positive infinities, we're happy. Or if both of those things go to 0, so both of those sequences go to 0, then the limit of the quotient of the two is the limit of the derivative of the functions, the quotient of the derivative of the functions, and this is sort of has changed to an x, right? So as x goes to infinity, if I have the limit of the derivatives, then I can find the limit of the originals as well. So L'Hopital's rule was basically a question of how fast does it go to infinity, or how fast does it go to 0, how fast does it go to infinity in this situation. And the idea is that that's all that matters. It doesn't matter where they're sort of a lot of the function values necessarily. What really matters is how fast are they going there, and so that rate of change is enough to tell you what the limit is in the end. So that's great. So that's good. We sort of had this L'Hopital's rule. The stuff that you're probably less familiar with are some of the variants of L'Hopital's rule. So if I have a function that converges to 1 and my second function converges to infinity, then I'm going to end up with a 1 to the infinity power. That is going to be able to be found in the limit, just like a 0 to the 0 would be, and also an infinity to the 0 would be as well. So those three indeterminate forms can be found, limits can be found using this method. And so what we do is we basically say, okay, so let's just sort of set this thing equal to e to the L, take the natural log of both sides. What happens with the gn is g of n pulls outside because it's an exponent. I have a natural log of f of n. Then I put the g of n into the denominator of this fraction as a -1 power. And then I get natural log of f of n over g of n to the -1, limit as n goes to infinity. And in this last case here, you sort of look at it, no matter which one of these cases I'm in, either I end up with a 0 over 0 or I end up with an infinity over infinity. And so that's great. So like in the first case, for example, f of n goes to 1, natural log of f of n goes to natural log of 1, natural log of 1 is 0. G of n goes to infinity, g of n to the -1 is 1 over that. 1 over a big number is a really small number. So it's a 0 as well. So I get 0 over 0, and I can apply L'Hopital's rule. So I can apply L'Hopital's rule to this thing and do a chain rule on the natural log and a chain rule on the -1 power. And then I end up getting what I need to do. So let's give you an example to sort of see this. So you can see the inside of this thing goes to 1. The outside of this thing, the exponent goes to infinity. And so I can apply this rule. And so what I get is I'm looking for my L. L is the limit as n goes to infinity of n times the natural log of n plus 6 over n. And now divide both of the terms, or so the bottom of this thing as by an n to the -1. So I flip this n to the denominator. So I have the limit as n goes to infinity of the natural log of, and I'm going to simplify this, it's going to be 1 plus 6 over n divided by 1 over n, or n to the -1 power. So I actually want, that's 1 over n, but it's also n to the -1. It's easier to take the derivative of n to the -1 than it is 1 over n potentially. So along those same lines here, I'm going to make that 6 times n to the -1 as well. Okay, so now I differentiate the top and the bottom because I've got a natural log of 1 on the top that goes to 1, natural log of 1, which is 0, and then the bottom goes to 0 as well as n goes to infinity. So I differentiate top and bottom. I end up with 1 over 1 plus 6 over n times the derivative of the inside. Derivative of 1 is 0, derivative of 6 times n to the -1 is -6 to the n to the -2, all over negative n to the -2. So I differentiate both separately, and I take the limit as n goes to infinity. The first term here goes to 0. I can cancel my negatives and my n -2s. This whole thing ends up being just 6. So I just have this thing, this one term left. So I have 6 in the end. So L is 6. So the limit of this thing converges to e to the L. So e to the 6th. And this comes from the fact that we took this natural log to pull the exponent in front. And so to undo the natural log, I have to take e to that power in order to get it to work out. Okay. So I guess it's sort of surprising, but not really surprising. We've got a sort of sequence of fractions here that exponentiate and get closer and closer to e to the 6th. And so as you sort of plug numbers in here, the bigger numbers you get, the closer you're going to get to e to the 6th. Okay. A little bit more terminology here. My sequence is increasing if every term after each successive term is bigger than the previous one. So for example, 1, 2, 3, 4, 5, 6, 7 is an increasing function or an increasing sequence. A sequence is non-decreasing if it's at least as big as what it was before. So for example, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. So I can either stay the same or go up, but I can't go down. So it's non-decreasing, not decreasing. It is decreasing if it's going down for all n. So it's 2, 1, 0, -1, -2, -3, and so on. It is non-increasing if it's at least going down or the same. So it's going to be 0, 1, -1, -1, -2, -2, -3, -3, and so on. And so that would be a non-increasing sequence. And then we call a sequence monotonic if it is either non-increasing or non-decreasing, meaning it either stays the same or moves, but only in one direction. And that direction is either increasing or it's decreasing. And so then that, as long as it's doing same or increasing or same or decreasing, it's monotonic. And so monotonic, meaning essentially one direction in that case, a monotonic sequence is something we really will be able to do some stuff with. A sequence is bounded above if there's like a big number so that all of your values of your sequence are less than that number for all choices of n. So in particular, if you have, say, a decreasing sequence, it is bounded above. It's bounded above by the first term in your sequence. So in the situation 2, 1, 0, -1, this is bounded above by 2. So 2 is the sort of upper bound of this thing. It is not, however, bounded below. So bounded below would be a small number so that all of your numbers are bigger than that number for any choice of n. And it's bounded if it's bounded above and below. So none of the sequences I've given you here are both bounded above and below. So you can sort of see it's either going to shoot off towards infinity or sort of go down towards negative infinity, but none of them are going to stay in between two bounds. They'll be bounded maybe above or bounded below, but not bounded in both. So what we're going to do here is we actually get something from this. A bounded monotonic sequence converges. All right, so I'm going to pause for just a second and let you think. So bounded monotonic sequence. So the sequence has a biggest value and a smallest value, and it's moving in one direction. And so basically, we can kind of say, well, if you've got a biggest value and you're non-decreasing, you're increasing, you're not going to ever go beyond that value. So not shooting off to infinity, you're going to go towards something. So there's some convergence in this sequence. It's going somewhere. And so if it's bounded and monotonic, we have a convergent sequence. Other things we might need, a type of sequence. And so one type of sequence that we can talk about is a geometric sequence. And this happens if there is a multiple that gets you from one value in the sequence to the next. So if you can multiply by r each time you want to go to the next term in the sequence, then that's going to be a geometric sequence. If r is less than 1, the absolute value of r is less than 1, this sequence will converge to 0. And if it's bigger than 1, then the sequence is divergent. If it's equal to 1, it's convergent to, in fact, c. And if it's -1, it's divergent because it actually just bounces between positive and negative values. And so it's not actually going to go anywhere. It's not going anywhere nice. It's going to be either c or -c, c or -c, c, -c, and it's going to bounce between the two. And it's not going to go anywhere in my sequence. Right. We're also able to get what's called the squeeze theorem. So the squeeze theorem for functions we had, again, was just about limits, and it was about sort of the limit on the outsides matching the limit on the inside. So it's the same sort of deal. So if I have 3 sequences, the middle sequence bounded on either side by the upper sequence and the lower sequence. If the upper and lower sequences go to the same place, then the middle one also goes to the same place. So here, as long as an and cn converge to the same L value, the middle one also converges to the same L value. Cool. And then finally, growth rates. So these functions here are listed in order of sort of slowest growing to fastest growing. And so what you can do is if you have a quotient of these things, you look on this list and you say, which one is further along in the list? If the top is further along in the list, then the sequence is actually going to be divergent and goes to infinity. If the bottom is further on in the sequence, it's going to go to 0. So if it grows faster, the top grows faster, it goes to infinity. If the bottom grows faster, it goes to 0. And so this is our sequence or our list of functions here. There's one in here that's a little bit different than what you've seen maybe before, n factorial. N factorial is the product of all numbers from n downward, and we don't have this in the function sense. So this is actually a list that you can sort of plug in functions, and this actually works for functions as well, except for the factorial. The factorial is not defined for just a general integer or a general non-integer value. So here, because we're talking only integers, the factorial is defined, and in fact, it's sort of a nice positive integers. Factorials go down from there. And so you take the say 6 times 5 times 4 times 3 times 2 times 1. So 6 factorial is just going to be the product of 6 times all the numbers preceding it. Okay, and you can calculate what that is. It's, let's see, 6 and 36 and 4. And so you just get a big number from that, and then you go from there. All right. Cool. So what I will do now is sort of just leave you to go try that homework assignment. Let me just briefly say here, so for something like this problem, you're going to look at this and say, okay, it looks like that L'Hopital's rule stuff that I was talking about. And so you're going to say, oh, okay, so that means I have an L, I have this limit, n goes to infinity. And I might even sort of think of this as like n halves and ignore the square root. And then I kind of go from there, n over 2, and then the natural log of 1 minus 1 over 21n, and then I go from there. All right. And so if I go from there, what am I going to get? So then I take this n over 2 and I put that in the denominator. So I flip it, make it a minus 1 power. And so that's going to be the limit as n goes to infinity of the natural log of 1 minus 1 over 21. I'm going to actually make that n to the minus 1 just to make my life a little easier when I differentiate, divided by 2 n to the minus 1. And so n over 2 to the minus 1 power is 2 over n, which is 2 n to the minus 1. So that's why I flipped that. Now I look at the top and the bottom and I say, okay, so now the top, as n goes to infinity, this goes to natural log of 1, which is 0. And the bottom, as n goes to infinity, this goes 2 over n. 2 over infinity is essentially getting closer and closer to 0. So I get a 0 over 0. I can do L'Hopital's rule. So I differentiate the top, differentiate the bottom. And again, I do not do like a quotient rule. I just differentiate the top, just differentiate the bottom. So the top here becomes 1 over 1 minus 1 over 21 n to the minus 1 times the derivative of that is 0 for the derivative of 1, and derivative of minus 1 over 21 n to the minus 1 is positive 1 over 21 n to the minus 2 divided by negative 2 n to the minus 2. So derivative of the denominator as well. The n to the minus 2's cancel. The minus 1 does not, and the minus 2 and the positive 21 go together. And then the limit as n goes to infinity, this thing here goes just to 1 because this denominator goes to 1 minus 0. And so that just gives me 1. So overall, this just gives me 1 over 42. So overall, I just get 1 over 21 divided by negative 2. So I should just get negative 1 over 42. And this was the limit L, meaning that I needed to take the natural log of both sides. So I should have that this thing converges to e to the L power. So that's e to the negative 1 over 42. Okay. So for these, you just want to sort of think, do I need a L'Hopital's rule? Is it going to be one of these with the exponents, or do I just do a straight L'Hopital's rule? Or is there something else that I need to do to get to where I need to go? Okay. So let me look at one more with you. So this one in particular, actually, let me go with this one first. I look at this one and I say, hey, look, those are two functions that look like the ones that I had in my growth rates table. And in particular, it's a power of natural log and a power of n. So I go back up here and I say a power of natural log grows slower than a power of n. So the power of n grows faster. That's the numerator. Since the thing in the numerator goes faster, this thing diverges to infinity. So those are pretty straightforward. You basically just have to look at that table or that list and say, all right, where is this? Where are these two things in the list? And then I go from there. All right. Then finally, we look at something like this. This one is not quite the L'Hopital's rule that we were doing before. It's actually like a subset of that L'Hopital's rule. So it starts when we look at the, we have the product. Limit of the product is the limit of the natural log, or the term on top over the term on the bottom to the minus 1. So what we have here is a product that goes to, looking at this, as n goes to infinity, sine of a 9 over n goes to 0. So this is like infinity times 0. And so what I'm going to look at here is I want to take the limit as n goes to infinity of sine of 9 n to the minus 1 divided by n to the minus 1. So I put this multiplication of n into the denominator, and you'll sort of get used to finding which is the best, but here I see this is the best because the derivative of sine will have an n to the minus 1 in it. So when I differentiate that, I'll have an n to the minus 2. That n to the minus 2 will cancel with what I get when I do the denominator derivative as well. So I differentiate the sine. I get cosine 9n to the minus 1 times 9, and it's negative 9, n to the minus 2. So differentiate the inside as well. And now I have divided by negative n to the minus 2. The n to the minus 2's cancel, the minus cancels. And now cosine of 9 over n, as n goes to infinity, that goes to 0. So cosine of 0 is 1. So this whole thing ends up just being 9. And here I do not have to take e to that power because I skipped the step where I took the natural log. So I didn't have to do a natural log. I was already at the product. So to go from there, I just look at that. That's the actual limit. So here I don't have an e to the 9. I just have 9. So 9 is the limit here because it does not have to go through that natural log to bring the exponent in front. And so there's no exponent here. We're just left with the limit being what the limit is when we calculate it from here. Okay, cool. So that's that for today. And let me know if you have any questions. We'll do more next time, and we're going to talk about a little bit of series next. All right, thanks.